In this talk, I would like to give you a geometric interpretation of adversarial training, and in particular, I will relate it to a very nice non-local geometric problem. And what I will speak about today is joint work with Nicolás García Trillos and Ryan Murray. And yeah, so let's get started. So first, this is the outline of today's presentation. I will begin with a motivation, what adversarial training is. Probably I will keep that a little bit shorter because it was already introduced by Tim. And then I will sort of speak about the geometric analysis that we did. First, I would like to sort of highlight some differences between asymptotic and exact regularization. And then I will sort of explain the non-local geometric quantities that are connected with adversarial training. Then I will present some existence and regularity results on the problem. And in the end, I will conclude the talk and give an outlook on what's next in this field. Okay, so let's get started with what is adversarial training and why is it interesting? And for this, let me just briefly recap the setting of supervised learning, which Tim has already done, but still I would like to set my own notation and so on. So in supervised learning, you are concerned with an input space X and an output space Y. And in today's talk, I would like to think about them as being abstract metric spaces, separable, but they can be general metric spaces. They can be RD, but they can also be a graph or whatnot, right? And then in addition, you're given some data, and this data is typically modeled by a probability measure mu, which is a probability measure on the product space of X and Y. And so basically the X marginal of mu explains or encodes the locations of the data points in the input space, and the Y marginal encodes some sort of labels that these data points might carry, right? And for instance, in this illustration down here, the measure mu is an empirical measure. So it's empirical in the X coordinate, so it corresponds to Dirac deltas located at some points, and then the Y marginal corresponds to the labels that these points have, and so these labels could be, for instance, values between -1 and 1, right? But in principle, this measure modeling also allows that a point has two different labels at the same time, right, with different probabilities, for instance. Okay, then in addition, you have to specify a space of hypotheses, which is nothing but a set of functions mapping from the input space to the output space. And you would like to use these functions to sort of solve the supervised learning task. But for this, you also have to prescribe a loss function L, all right. And now we can formulate the supervised learning task as it is, which is the following. So you want to find a hypothesis, so a function u in this space C, which minimizes the empirical risk over your training data. And so the empirical risk is nothing but the expected value over this probability measure mu of the loss function applied to the output of the hypothesis and the label y, sort of, right? So this loss function compares how well the output of the hypothesis coincides with the label, and then you want to minimize the expected value over this loss, right? And if you do this, you will get some function u which realizes this minimization problem, and this function u is then thought of as extending the data to the whole space. And if you plot the level sets of such a function, it can look like on this image down here, right? And this is sort of the prototypical task of supervised learning, which you also solve when you train a neural network, right? So let me give you some examples for these supervised learning tasks. The first one is a very easy one, where the class of hypotheses is just the set of linear functions, which can be written like this, right? And then this supervised learning just becomes linear regression. You can make this a little bit more complicated by composing a linear function with a sign operation, and this then gives you a so-called linear classification. So here, the optimal hypothesis that you would like to compute sort of subdivides the space into two half spaces corresponding to two different classes, right? And then by sort of concatenating a lot of these nonlinear functions, you will then get the class of neural networks, which is unarguably the most popular hypothesis set nowadays. So a neural network is, in general, just a composition of capital L many nonlinear functions, phi L, where each nonlinear function phi L has a very specific form. Namely, it's given by a linear function composed with a nonlinear activation function, sigma L. Right? So this is the space of neural networks. And of course, I don't have to tell you that neural networks are extremely popular because they manage to solve difficult tasks very efficiently, as we've seen before. However, as already indicated in the first talk by Tim, they also come with some intrinsic problems. And the biggest problem is probably their sensitivity with respect to adversarial attacks. Right? So there is this possibility that you have some image, which is, let's say, correctly classified as a panda, but then you can compute some tiny noise perturbation such that if you add the two things, so the image and the noise, you will get an image which looks precisely the same. However, it's then misclassified as a gibbon in this scenario with a very high confidence. So Tim has already explained to you that this can happen. And let me just mention that in this situation that typically what people do to compute this noise is a very simple thing. They just compute the gradient of the loss function at the point x, which is sort of this panda image, right? And then they take the pointwise sign operation of this gradient and add it to the image. And this is like a one-step attack, and it gives you these kind of shocking results, right? And mathematically, adversarial attacks are formalized as maximization problems, as mentioned by Tim. So what you would like to do is, starting from a point x that you would like to attack, you want to find another point x tilde, which is in some epsilon ball around x, and which maximizes the loss function between u of x tilde and the label y. So this is an untargeted attack. Okay, so let me now recap what adversarial training is. So let's first look at how to derive adversarial training, and the idea is basically very easy. So what you do is the following: you start with the empirical risk minimization problem that we've seen previously, where one just would like to minimize the empirical risk over all hypotheses in the space, and then in order to sort of defend against adversarial attacks, the idea is to replace this data point x with an adversarial attack. That's the only thing that you do. And this then leads to the following problem. So you still would like to minimize an empirical risk. However, this risk is now the adversarial risk. So you replaced x here with this x tilde down here. And x tilde is chosen sort of in the worst possible way, realizing this adversarial attack. And this is adversarial training. Empirically, it works extremely well. However, it's not at all analyzed, I would say, or there's very little analysis on this problem. However, from a mathematical level, it's just a robust optimization problem. So there is something that one should be able to do. And let me first explain you a little bit how people try to understand adversarial training, or the effect of adversarial training. And for this, let's go to a very easy framework where we assume that this epsilon ball is just the epsilon ball in some norm. So we have a norm perturbation. And then we also assume, for simplicity, that the gradient of the loss function with respect to the input variable is Lipschitz continuous. Okay. And what you can do in this setting, you just do a Taylor expansion of the adversarial risk. So you take the adversarial risk, which is this expression here, and you Taylor expand it in x, in the x variable. Then you take, and then what you end up with is this expression here, where you suddenly notice that you have the standard empirical risk, which does not include any adversarial attack and no epsilon. But then you have plus epsilon times a regularization functional, which is now the expected value of the norm of the gradient of the loss function. And then you have some higher order correction terms which scale with epsilon to the power of 2, right? So you might think that adversarial training is basically regularized risk minimization, where the regularization functional is this total variation term, right? And this sort of strongly relates to the question that Yuri asked in the first talk: shouldn't we do some sort of BV regularization? And with this, I would like to make the point that yes, adversarial training basically does something like TV regularization. However, this statement is very imprecise from a mathematical point of view, right? Basically does something like, it's not a statement that we are happy with as mathematicians. And so let's see whether this asymptotic expansion is actually a good thing, a good model to work with. And here I would like to make the point that it actually is not. So if you replace adversarial training by its first order Taylor expansion, namely this variational regularization scheme up here, this does not capture the essence of adversarial training. And I would like to support this claim with a simple example taken from the original adversarial training paper by Mari and co-authors. And I always use this figure because it's just the best figure that you can use for adversarial training. So here the situation is that you want to separate blue points and green points. And so the explicit solution to the empirical risk minimization problem here in this setup is just this linear classifier. However, it turns out that the linear classifier is not adversarially robust, because as you draw small epsilon balls around your data points, some of these epsilon balls intersect the decision boundary, and hence you'll be able to generate misclassifications at these intersection points. And what adversarial training now does is to adapt the decision boundary in such a way that these attacks cannot happen anymore. So you will get a new decision boundary which looks something like this. So this is the effect of adversarial training. However, if we were to solve this regularized problem up here, we would actually do nothing at all, because this linear classifier has already the smallest total variation that you could ask for. And the problem sort of is that epsilon, sort of this expansion is only valid for very small values of epsilon. However, if I want to attack, I might choose a bigger value of epsilon, which is not very close to 0. And then this asymptotic expansion becomes wrong, and TV regularization is not the right model anymore. Okay. Of course, there are ways to correct for that. The first way is to simply include higher order terms in epsilon. Right, so I mentioned previously that you have some additional terms which scale with epsilon to the 2. You could just include their precise expression into the regularization problem, and this then leads to something which is called curvature regularization, where you're basically also penalizing the let's say the Hessian matrix of the loss function. But also this is only an asymptotic expansion, so whenever epsilon is rather small, this will become a bad model compared to the original adversarial training problem. And therefore, I propose to look at exact regularization. So that means to try to understand whether adversarial training is a regularization method, however, with respect to a different regularization functional, which is not this total variation term up here. And indeed, it turns out that this is the case. And this is what we showed together with Nicolás and Ryan. Namely, adversarial training equals a regularization method. So you can write it like this. You can write it as the sum of the empirical risk plus epsilon times the regularization functional. And this regularization functional is a non-local total variation. And to see this, first let me tell you how we do this rewriting. And this is sort of completely trivial. It's just a tautology. You define this J epsilon functional in such a way that the identity here is trivially true. So you basically just take the adversarial risk and you subtract the empirical risk, and this way this identity is always true, since we also divide by epsilon here and multiply by epsilon. So there's nothing behind this. But then sort of to understand what's going on, you have to analyze what is this functional J epsilon. Can you give meaning to this functional? And in this talk, I would like to remain in the setting of binary classification, where one can actually nicely classify sort of this regularization functional. So in binary classification, the labels are in 0, 1. Then the class of hypothesis is just a set of characteristic functions, which is of course a good model for binary classification. And the loss function in this case is just the absolute value of the difference. Okay, you can generalize all of this, but this is sort of the nicest interpretation that you can give to the problem. And in binary classification, it turns out that that this regularization functional J epsilon, which I defined previously, is nothing but a non-local and data-driven perimeter. And it has this form. So this is the perimeter term that pops up. And it consists of two volume terms. So this is a volume term and this is a volume term. And those two terms measure the volume of a strip with width epsilon around the boundary of the set A. And this is sort of an outer strip, and this is an inner strip with width epsilon, and you add up those two volumes. And the measures, rho 0 and rho 1, that you're using to measure these volumes are just the conditional distributions of the data points which have the label 0 and which have the label 1 defined down here. So for people from calculus of variations, this looks very similar to the so-called Minkowski content, which is typically defined by sending epsilon to 0 in this expression. However, we don't want to do this because we want to work in this non-local regime. Okay, so now we've discovered this perimeter. Let me now give you some analytical results on the perimeter, and let me relate it to a total variation, which is also non-local then. So just to remind you, this was the perimeter that we've seen previously. And the first thing that we can prove is a very important convexity property, namely that the perimeter is a submodular function on all Borel sets of the metric space. And submodular basically means that this inequality is true. And this is an inequality which is also true for the standard perimeter, which is just a surface measure of a set. And sort of this justifies why we call this object a perimeter, because it's submodular. And another good thing about the submodularity is that it allows us to define a total variation. And the total variation is now defined using the co-area formula. So as you would do it in classical BV literature, you define the total variation of a function u as the integral over the perimeters of all the super level sets of u. Right? So this basically decomposes u into its super level sets and adds up all the perimeters. And this is a functional, that's for sure. However, it turns out it's a convex functional, and this is thanks to this submodularity issue up here. And in addition, it's positively homogeneous. And so this really looks like a total variation, and indeed it has all the properties that also the standard total variation has. And we can also characterize this functional, and it has the form down here. So this is the total variation applied to a function u. It's given by the sum of two integrals, which are kind of similar. One is with respect to the measure rho 0, the other one with respect to rho 1. And you sort of have these terms here with the supremum of u minus u of x, and you divide this by epsilon, and you have the same thing over here with the infimum. So basically, this total variation is the integral over finite differences of u evaluated at x, right? And these finite differences are taken in an epsilon neighborhood. And this is why we call this thing a non-local total variation, because it's really something like the integral over the norm of the gradient. However, you replace the norm of the gradient with this non-local finite differences, basically. Okay, so this is the TV functional. And now we can start the machinery. We can try to prove existence using the standard method of calculus of variations. And what we get is the following nice theorem. Namely, the adversarial learning problem that we started with, the one over here with the perimeter regularization, it has an exact convex relaxation, which is this problem here where we now minimize over functions instead of sets, which have values between 0 and 1, and we penalize these functions with the total variation over there. And with exact convex relaxation, I mean that whenever you take a solution of this problem, you take a set A, then you can look at the characteristic function of A, and this solves the second problem. And whenever you take a solution of the second problem, you can take a super level set solution, and this will give you a solution of the first problem. So you can really go between these two problems. And you can also, most importantly, you can prove uniqueness of, you can prove existence of solutions using the standard method. Right, so the proof techniques here are somewhat intricate because you have to work a lot to prove existence. And the main issue is the lower semi-continuity of these functionals here. And for this, one has to relax the total variation to a suitable space of Lebesgue functions on the metric space. One has to construct a so-called Vitali measure nu, construct precise representatives, and then finally one can prove lower semi-continuity. So there are some technical steps here which I don't want to go into detail about. Let me just mention sort of the main ingredients here for the proof. And so the first question that you have to ask yourself is, what is the right space of solutions that you should be working with? Is it the space of bounded functions with respect, or is essentially bounded functions with respect to this measure rho, where rho is the sum of these two guys appearing in the total variation? This might be a good guess, but it turns out that this is not the case. This is not the right space of solutions. What you have to do is you have to work in a space with respect to a measure nu, which is somewhat bigger than the measure rho. And the reason is that, so if this is the support of rho, you're taking these suprema here over these epsilon balls. And so you should be working with a measure which is supported in this epsilon tube around rho. And this is where this measure nu is supported. So you have to construct this measure nu such that things work. And then once you've done this, you can characterize the lower semi-continuous envelope of this total variation functional, which looks very similar. You just replace the suprema and the infima with the essential suprema and the essential infima with respect to this measure nu that you have to construct. Okay, so this is just a technicality in order to prove existence of solutions. And once you've proved existence using this regularizer, you can then go back to the original one by using precise representatives. Okay, let me now very briefly also sketch some regularity results that we can prove. For this you have to use mathematical morphology. If you have a set, you can define like the outer epsilon tube and the inner epsilon tube. You can define an opening and an closing. So just as an example, if you have a square, for instance, then the opening of this square, for instance, is a square with soft corners, right? So this is the opening of the square, whereas the closing is the same thing. So these are morphological operations, and you can also define regularity with respect to such an epsilon parameter, namely whenever you can fit a ball from one side, right? So if you take the square again, you can always touch this with balls from the outside, but you cannot touch it with a ball from the inside at this point, right? So this is an outer regular set, but no inner regular set. Anyhow, and so what we could prove here is, let me jump over this a little bit more quickly, is then sort of whenever you have a solution to the problem, any solution, any set B, which is between the opening and the closing, is also a solution. So we don't have uniqueness, but you can construct competitive solutions. And you can also prove existence of maximal and minimal solutions with respect to set inclusion. And in addition, we can also prove some regularity, namely that you can construct a Hölder continuous set. Right. So let me now go to the conclusions of this talk. And the first thing is that we saw that adversarial training is equivalent to a non-local total variation regularization. So this is the right model. And then we've also seen that using a clever relaxation to a functional analytic framework, one can prove existence of solutions, which is also the first time that this has been done. And yeah, regularity issues are studied using morphological operations where you sort of blow up sets or you shrink them and you see how the functional behaves under these operations. And there are a couple of things left. So the first thing that's left is, for instance, investigating gamma conversions in the epsilon parameter. So as you send epsilon to 0, you would expect that the perimeter converges to some sort of local but weighted perimeter. And also an improvement of the regularity statements might be thinkable. And Another thing which is interesting is you can study a so-called Almgren-Tyler-Wang modification, where you change the empirical risk by sort of multiplying it with this distance function to the decision boundary, which gives some extra weight to points which are far away from the decision boundary. And finally, since Tim has talked about Lipschitz regularization quite a while, and I talked about BV regularization, what should you do? Should you do both? This is a big question, and it turns out that probably you should do both at the same time, adversarial training and Lipschitz regularization, and this is then referred to as worst case adversarial training, and this might also be an interesting thing to consider. All right, so I'm done. I would like to thank my co-authors who are depicted here. Here you can find the preprint if you're interested, and now I'm happy to take your questions if there are some.